Today we're learning about a certain type of discrete probability distribution. It's called binomial probabilities. And you'll be able to tell if it's this situation because you either win or lose. There's either success or failure. Each trial also has to be independent. And let's just do an example so you can see when a binomial experiment would apply. So if we were spinning this spinner, either you win or you lose. That's classic binomial. It's also independent because landing on a win doesn't affect your next spin, and vice versa. So let's say we spin it 5 times. What's the probability that you win exactly 2 times? So n is the number of times that we spin. R is the number of times that we win. P is the probability that you win. And if you look at that spinner, it's a 75%, nope, a 25% chance that you win. Q is the probability that you don't win. And so that would be the 75% chance that you don't win. And like I said, it is independent because each spin is not going to affect the next spin. Here's another example of a spinner. You spin this spinner 3 times. You win each time you spin a square. Complete the table for the probabilities. So spinners are always independent. Either you spin a square or you don't. That's what makes it binomial. There's 2 outcomes, either square or not square. And there are actually 8 different things that could happen. On these 3 spins, we could spin square, 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 not a square, square, not a square, square, right? So that just shows all of the different outcomes, sort of like the tree diagram. Let's just count how many times you win on each of these. So fill this in. On the first one, if you got a square, 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 you won 3 times. On this one, you win 2, 2, 2, 1, 1, 1, and none. And so what we're going to do is if we want to find the probability of square and square and square, we're going to take probability of a square times probability of a square times probability of a square, which will just be 3 of those, right? I'm going to write this down even though it's probably not necessary. Anything to the 0 is just 1, so that doesn't affect it. This just signifies that we didn't get any loser spins. We had 3 winner spins, 0 losers. Similar here, I would have 2 winners followed by that loser. This one I'd have the 0.25, the 0.75, and then the 0.25. Since when you multiply the order doesn't matter, I'm just going to write this one the same as the last one. So anytime you have 2 successes, you're going to be able to write it as probability of success 2 times with 1 failure. And I filled in the rest of those like that too. All right, so we want to try to find a pattern so we don't have to actually write out this dumb table every time. This one comes out to 0.015625. Each of these come out to the same answer, right? And it is 0.046875. So we'll just kind of add all those together, and that'll be the probability of winning twice. Same thing here, if we add all of these together, that'll be the probability of winning once. And then this last one, which comes out to 0.421875, that's our probability of winning no times. I guess I could have calculated this one for you. This one turns out to all 3 of these down here, 0.140625. 3 of those. So the moral of the story is, since there was only 1 arrangement of 3 successes, we just take 1 of that probability. But there were 3 2-success options, right? There were 3 1-success options, but then just 1 of those. So that's our table. So this cute little formula is the thing that keeps us from having to make that table every time. The key thing being right here, that is our counter that's going to count how many times you can expect success in n trials. And these should look sort of familiar, that probability of winning times the probability of losing, and to those powers that represent how many wins and losses. Here's an example. Find the probability that you get 2 squares. So we're finding the probability that r equals 2. So we would do 3 spins, choose 2, times probability of getting a square to the r power, times the probability of not getting a square to the n minus r power. And so that just really calculates what we did on the previous page, and it comes out to 3 times. Remember, there were 3 ways to get 2 successes. And I got 14.1% approximately. So here's another one. We haven't made a table for this one. Find the probability that you get 4 B's. 4 B's in 7 spins. So 7C4. That's all the different ways we could get 4 B's. Probability of getting a B 4 times. Probability of not getting a B 3 times, right? So 12.8% is what I got. And then the last one, probability of getting 1x in 6 spins. So 6 spins, we want to get 1x. Probability of getting an x, only once, times the probability of not getting an x the other 5 times. Here's an example that maybe somebody in agriculture would be interested in. You plant 5 pumpkin seeds. Each seed has a 70% chance of maturing into a healthy plant. What is the probability that you get at least 3 healthy plants? And we have to assume that each seed is independent. So we're planting 5 pumpkin seeds, right? That would be the number of trials. And we're looking for, okay, this is a little different. We're looking for the probability of at least 3, which would be the probability of 3 being healthy, or 4, or all 5, best case scenario. And I've trained you hopefully to that when you see the words at least, you think about the complement. So what's the complement of r being greater than or equal to 3? And that would be r being less than or equal to 2, if you think about it. So that would be the probability of 2 or 1 or none, which actually wouldn't save us any time in this case. So we're probably just going to do the original problem then. So we'll do probability of 3, probability that r equals 3, which would be 5C3, 70% chance for 3 of them. And if the other 2 die or are unhealthy, that would be okay. Maybe we'll get 4 healthy plants. Maybe all 5. Oops. And since I was saying this is an or, right, either 3 or 4 or 5, we would just add all those together, and I'm getting an 83.7% chance of having at least 3 healthy plants. I have a couple of different ways for us to calculate that, because that could get a little tedious at times. So the first way is there's a table, and it's in the back of the book, but you don't need to find it right now. But it'll say binomial probability distribution. And basically what it has is it has your n and your r right over here. So in the pumpkin case, there were 5 seeds, and we were wondering what's the probability of getting at least 3 to maturity. And then across the top here are the probabilities of success, and we're looking at the 70% probability. So if we follow the 3, 4, 5, in the 70% likelihood, this little spot right here gives the probability of 3 or 4 or 5. And so then we can just take the 0.309 plus the 0.360 plus the 0.168, and we still get that 83.7%. There's a little more rounding in this table, but it serves the same purpose. That just makes it a little quicker so you don't have to type it in every time. And finally, there is a button on your calculator that can calculate each of these real fast. So Binomial PDF is under second vars, which is the distribution area of your calculator. Binomial PDF. And you're going to list the N, and then the P, and then the R. NPR. So just another way of finding probability of 3 or 4 or 5, and then adding all of those together, 83.7%. And hopefully this last thing isn't going to confuse you, but hopefully it will help you a little bit more. In the same menu that you just went to, that second vars, under the binomial PDF, you probably saw binomial CDF, and that is called a cumulative distribution, and that's because it does accumulations. For example, what if I were asking you to find the probability of up to 2 healthy plants? Anytime you have a probability that's situated that way, R is less than or equal to something, you can use the cumulative distribution, which means it's going to do the accumulation of the probability of 0, or of 1, or of 2. See how it's accumulating up to the probability of 2. And it's the same thing, N, P, R, but this time that stands for the probability, those 3 probabilities added together. It gets a little tricky if I had a question like this, if I wanted to know at least 3, which would be greater than or equal to 2, or if you think about it, you could also say that's greater than or equal to 3, at least 3. See, CDF doesn't work on this, so what we would have to do is figure out what the complement of that is. And the complement of greater than or equal to 3 is the probability of being less than or equal to 2. So this can be done, the less than or equal to, can be done with a CDF, and it's the one that we just did up above. So that would be 0.16308. And so the probability of the complement of that, which would be 3 or more, would be 1 minus that. So it's just a little bit trickier to use that button for greater thans, but it's still doable. All right, you guys do your best. Thank you.